In the last video, we started looking at nucleophilic addition reactions where we were adding a nucleophile to the carbonyl carbon of an aldehyde or a ketone. The last thing that we did was look at a generic mechanism for adding a nucleophile to the carbonyl group of either an aldehyde or a ketone under acidic conditions and also under basic conditions. And we made a list of some nucleophiles for the acidic and basic mechanisms of this reaction. The next few sections of your textbook are going to look more specifically at the nucleophilic addition reaction, and he has grouped the reactions based on the type of nucleophile that will be doing the addition. He has based it on the atom, like the oxygen atom, that is attacking the carbonyl carbon of the aldehyde or ketone. So section 20.5 is on nucleophilic addition reactions where oxygen is the nucleophile in the addition reaction. And there's two of these reactions. One is the formation of a hydrate, and this is a hydrate over here. You can see it's got two OH groups on it attached to the same carbon. And the other reaction is the formation of an acetal. This is an acetal, and you can see it's really similar to a hydrate. It has OR groups instead of OH groups. So the formation of the hydrate reaction is kind of particular. It only works with formaldehyde, no other aldehydes, no other ketones. That's because it's a difficult reaction. It does not want to work, and so it's only possible to do this reaction with the smallest of all of the aldehydes and ketones. So we're going to draw a mechanism for this reaction under both basic conditions and acidic conditions because it can occur under both conditions. When we are doing this reaction under basic conditions, remember that bases are negatively charged, like for example hydroxide. We always remember that that's a base. So when we do a reaction under basic conditions, we should always see our reactants and our reagents negatively charged or just neutral, one or the other. So if we're looking for a negatively charged nucleophile to do this reaction under basic conditions, we're going to see hydroxide as the nucleophile for this reaction. And remember, under basic conditions, the negatively charged nucleophile attacks the positively charged carbonyl carbon, opens up the carbon-oxygen double bond, and we get the carbon-oxygen double bond has been opened up. We've got an extra pair of electrons on the oxygen, so the oxygen has a negative charge on it now, and we have added an OH group to what used to be the carbonyl carbon. This is followed up with water. Water will protonate the O-, and we get the hydrate. Now I've drawn it a little bit different, but it is the same thing as what you have in the example up above. So there's the mechanism for that reaction. That's pretty straightforward. Let's do the same reaction down here, but this time we're going to be doing the reaction under acidic conditions. So whenever we do a reaction under acidic conditions, that means that all of our reagents and all of our reactants need to be positively charged or neutral, but no negatively charged things at all. And one of the ways that you can remember that, the most common base that we're used to the most common acid that we work with is H3O+, positively charged. So that'll help you remember that you need to have positive charges on everything or neutral when you're doing an acidic mechanism. So under acidic conditions, whenever you have an oxygen in a reactant and you're under acidic conditions, the very first thing that happens always is protonation of that oxygen by the acid. So the first thing that's going to happen is the oxygen of the carbonyl group gets protonated. And that leaves us with water. So after this H3O plus loses its proton, it's just left as H2O. The oxygen of the H2O is the nucleophile. It comes up and attacks that carbonyl carbon, pops the carbon-oxygen double bond open. Let's draw this. We've added water molecule to what used to be the carbonyl carbon, and it's positively charged because it has 3 bonds on it, and notice that's okay. We're allowed to have positive charges under acidic conditions. The last thing that we need to do is bring in, let's say we'll bring in another molecule of water to deprotonate that oxygen that has a positive charge. So the acid catalyzed reaction has more steps to it. It is a little bit more complicated, but we end up with the same product.